Welcome. So now we're going to solve this question based on SMT and VMD, where we have been given that AD is a beam. Let us call it AD. We have a UDL between AB and inclined force at C and roller support at D and in support at E. So let us see how we can solve this. Firstly, we will draw the FBD of the following beam to find the support reactions, and then we will find the shear forces and then the bending moments at every point of the beam. This to find the SFD and BMD. So firstly, let us draw the FBD. The first step being drawing the FBD of the beam. So we have this, let us say, as your A, B, C, and D. At D, we have roller support, so we will give only one reaction in the upward direction in the R, D, Y. Let us for it, and we have hinge support at D, so we will give reaction both the reactions, which is a horizontal reaction and a vertical reaction. This is RAY, this is RAX, and there is a UDL which we need to convert into a point load, which will be simply be nothing but the magnitude of the UDL into the distance on which UDL is acting. So 100 into 4, which is 400, and it will be acting at the midpoint of the UDL, which is 2 from A, 2 meter from A, and 2 meter from B. And B to C is 4 meter, C to D is 2 meter, as given in the diagram. Also, we need to resolute the force at C, which will be 400 sine 60 and 400 cos 60. This will be the resolution of force, the 400 Newton force at C. So yeah, this is how you can draw your FBD. And after that, you can apply the equilibrium condition. So equilibrium conditions. So first of them will be summation of Fx is 0. Second will be summation of Fy is 0. And third will be summation of movement at any point is 0. So from the first equation, you will get like the reaction RAX is nothing but minus 400 cos 60, which is a minus 200. So which means that the reaction at EX is not in the right direction, which we have assumed it should be in the other direction. So just change the direction of RAX and the value of RX will become 400 cos 60. And applying the second condition that is applied here, we have RAY minus 400 as the UDL force, minus 400 sine 60 as the force at C, plus RDY should be 0. And if you solve this, let us solve this using calculator. We have 400 plus of 400 into sine 60. We have RAY plus RDY as a 746.41. So yeah, 746.41 is the value of RAY plus RDY. And next you can apply the movement condition here, which is a summation of movement at point A is 0. Because you can apply this condition at any point, let us say A, B, C, D. But for now we'll apply it at A because then the force at A will disappear, like RAX and RAY will not be there in our equation, which we want because we want to eliminate as many forces as we want in our equation. So we will apply it at A to eliminate most the forces. So we have 400 into 2 generating in clockwise movement. So clockwise movement will take it as positive and anti-clockwise will take it as negative. So you can change this, it won't affect your final equation. So we have 400 into 2. As a clockwise movement, we have a 400 sine 60 into 8 into 8. Again, a clockwise movement, so again a positive. And we have RDY into 10 as an anti-clockwise movement is equal to 0. So let us solve this again. We have 400 into 2 plus 400 into sine 60 into 8 divided by 10 is a 357. So our dy comes out to be 357.12. Let's call it 1 3. And we have a 746.41 minus This is 389. So RAY will be 389.28. Yeah. So these are the reaction RAY and RDY. So let us just check your calculation once again. We have 400.
Is 400 liters is props.
Okay, yeah. The calculation should be correct. So we have, let us just update your values which we got. We have 400 cos 60, which will be just 200. So just write it here. We have 200 as the RAX. We have 389.28 as the RAY. We have 357.13 as the RDY. And after we got the reaction forces at reaction support forces, then you can just calculate the shear forces and bending moments at every point to calculate your, to draw your diagram. So we will now do that we will find values of shear forces at every point. And whenever there is a sudden force, let us say at C there is a sudden force of 400, then you need to calculate just left of C and just right of C also to get a clear idea of how the shear force is varying at that particular point. So let us see shear force just right of A. So firstly, let us just get clear with the sign convention. We have shear forces. Then let's say you are considering forces on the left of the cross section. Then upward forces on the left of the cross section should be positive, and the downward forces should be negative. And if you are considering forces on the right side, then upward forces should be negative and downward forces should be positive. Just reverse the previous one or the left side one. So what I mean by this is, let us say you have crossed the line somewhere here, which is just right of A. You need to calculate that right at that point, right? Just right of A. So consider forces on the left, which is just one force, which is 389.28. So how do you decide its like the sign? So it is acting in the upward direction. So that is why the sign should be positive. Left side and upward. So it should be positive. That is how you can decide its sign using the sign convention. We have shear force at V, which should be 389.28 minus 400 because of the UDL. It should be, let us just calculate it. We have a 389.28 minus 400. It should be minus 10.72. We have shear force just left of C, which is a minus 10.72, and the shear force right of C is minus 10.72 minus 400 sin 60, because there is also this 400 sin 60 force. When you're just calculating on the right and considering force on the left, then you can, like, you cannot ignore that force, you need to consider that force. Which will give you 357.13 negative, of course. So yeah, shear force at just at such. So shear force just left of D will be same, then minus 357.13, and shear force at D will be 0 because there is a reaction of 357.13 at that point. So minus 357.13 plus 357.13 will become it to be 0. So we have this beam we have A, B, C, D, and the shear force at A is 389.28, at B it is a minus 10.72, at C it is minus 357.13, minus 357.13. Left of C it is the same, and left of D also it is same, and at D it is becoming 0. So you can just join it using straight lines, but not on the UDL part. The UDL part should be joined using inclined line, like something like this. So this should be a line. It's now looks like to parabola. Yeah. So this is how you can make your shear force diagram. As you can observe, like somewhere in between E and B, it is going to 0. We need to find that distance x also, because at that point the bending moment will be maximum, and we need to find that point. So let us firstly just quickly find out that point just before. So the trick to find that particular point where the bending moment is going to maximum is that just look at the force or the shear force at the starting of the union. So at the starting of the union, it was 389.28, and minus it should be 100 Newton per meter into some distance, like let us say x. It should be going to 0. So this is the simple like trick you can use, that try to find the force at the starting of the UDL, which you will obviously like get using the shear force calculation. And after you get it, just subtract 100x, which is the total magnitude of force for x length of the beam. So let us say there is a UDL of 100 Newton per meter and applying at a distance of x. So 100x will give you the magnitude of the force. So that is why minus 100x should be equal to 0. And x will come out to be 3.8928 from this calculation. So that x is nothing but 3.8928. Yeah. So just make it somewhere down here. Yeah. And we can now solve the question further. We have just to let us just take it as 3.9 instead of 3.892. Just take it at 3.9. It will be easy for calculating further. We have a bending moment at A and D as 0 because of the equilibrium condition. You can also try to calculate this using our FPT which we made. It will come out to be 0. It should come out to be here. So yeah, you can just write that bending moment at start and end of the beam is a 0 because of the equilibrium condition, unless there is a fixed support. So if there is a fixed support, it will not go to 0. We have a bending moment sign convention as whenever you are considering movements at the left, try to like take the clockwise moment as positive and anti-clockwise as negative. And whenever you are considering movements on the right, take the clockwise as a negative and anti-clockwise as positive. So we have a bending moment at A and D as 0, bending moment at some point, let us say 3.9 meter from A, which is we are claiming that it should be maximum. So let us see what it comes out to be. We need to draw the FBD for that point. So this is the force acting in the upper direction, 389.28, and the total distance is 3.9 up to that point. And here we need to calculate bending moment at that point, particular this point, let us say, and calculating from the force on the left we are doing right now. So we need to also apply this UDN, which is acting in the downward direction. So if you like convert this into the force value, which will come out to be 389.28, and it will be acting at the midpoint of this. So instead of 3.9, you can also like for now we'll take a 3.8928 for the force calculation. So yeah, you can just change this to be again 3.8928 because it is required to for calculation right now. So 3.8928 let us take, and it will be in the midpoint. So total is 3.8928, 8928. Yeah, you can also do that. We have a 389.28 into 3.8928 minus 389.28, because it is an anti-clockwise movement, that is why we are taking it as negative, into 3.8928 by 2, because the distance will be the total distance divided by 2. So the answer comes out to be 389.28 into 3.8928 into 1 minus 1 by 2, which is 1 by 2. So let us just calculate that using your calculator. We have 389.28 into 3.8928 divided by 2. We have a 757. 757.6945. So let us just write it here somewhere. We have 757.6945. Yeah. As we have calculated bending moment at some point x, at point x, let us calculate bending moment at B. Considering forces on the left, we have this is point B, so 389.28 into 4 in the clockwise, so that is why it is positive, minus 400 into 2. It is an anti-clockwise movement, so that is why it is negative. And 400 force is the CUDL force, into 2 is the distance. So if you calculate this, you will get 389.28 into 4 minus 800 as a 757.12. 757.12. We have bending moment at C. Let us calculate from the forces on the right, because there are very little force on the right. Just the one force, which is a 357.12 into 2, and it is an anti-clockwise movement. But now the right side we are calculating, so anti-clockwise should now be positive. So we have 357.12 into 2, 714.24, and bending moment at D is, we have already said that it is 0. So let us say this is our beam, which is A, B, C, and D. At A we are saying it is 0. At B we are saying at 3.9. See, to say this is 3.8928 from somewhere, like from E. It is maximum, which is at 750. 7.6945. We have at B, it is a 757.12. At C, it is a 740.24, and at D, it is A. So we know that whenever there is a median, it will vary as a parabola, the bending moment, and whenever there is not, it will vary as a linear line, as an inclined line. So this is how you can draw your bending moment diagram. So yeah, this is how you can solve your question. Thank you.